Welcome to the channel. In this session we will learn how to apply divide and conquer technique to find out the matrix multiplication with reduced time complexity. So whenever we are having two matrices A and B, A and B of n by n size, I can find out the multiplication of these two matrices. C is equal to AB is also an n by n matrix. So which I would be getting by taking the elements of ith row and jth column of A, ith row of A and jth column of B, and multiplying them to get all the elements of I and j between 1 to n. So we know the formula. C of ij is equal to sigma 1 to n A of ik into B of kj. So whenever we have uh, this kind of multiplication, I need to write the algorithm by using three for loops. One is for indicating the rows, the row of A matrix, and the other is for navigating through the column of matrix B, and the other is to maintain the position of the matrix C. So I can say that whenever I am having three for loops of size n, then it will be order of n cube. However, this order of n cube matrix multiplication time complexity can be reduced whenever we apply a divide and conquer strategy. So this has been proposed by a mathematician called Strassen, who applied the divide and conquer strategy to multiply two n by n matrices. And the main idea of this problem is to divide the matrix into submatrices so that it is having the dimensions of n in terms of power 2. So imagine that we have two matrices A and B such that each is partitioned into four square submatrices, and each submatrix is having the dimension of n by 2, n by 2 and n by 2. And this is how they look like. Matrix A and B, A11, A12, A21, A22, B11, B12, B21, B22, and if I am multiplying them, C11, C21 and C12, C22. So let us assume that for simplicity I am taking the unit matrix. Let us say 1 1 1 is my matrix A, and 1 0 0 1 my is matrix C. If I multiply with the unit matrix, I will be getting the same matrix like 1 1 1. So we know the row of A will be multiplied with the column, and then we will be getting this particular. So 1 into this element into this element plus this element into this element will be having, it forms the first element of the resulting matrix. So if I do that, in this particular scenario, observe, to get each element of the matrix C, I require two multiplications operations and one addition operation. Two multiplication here and one addition here. Like that I am having four elements here. So hence I require 8 multiplications and 4 additions. So the time complexity will be so this 4 additions is approximately proportional to my n by n matrix, whatever the dimensions of the matrix I am having. So hence, so whenever the time complexity T of n is equal to the constant whenever n is less than or equal to 2, otherwise it is equal to 8 multiplications for each n by 2 matrix, and n square number of additions, n square time complexity I require to perform the additions here. So hence, if I solve this equation, 8 into T of n by 2 plus Cn square, I would be getting the time complexity as order of n by order of n cube, order of n cube. Fine. So this I can find out by using divide and conquer generalization method. So I can write that h of n is equal to n power f of n by n power log a to the base b. So f of n is here cn square and n power log 8 to the base 2. So cn square divided by, so this I can write it as 2 cube, and this becomes n cube here. So I'm having c in terms of minus 1. So whenever it is minus 1, my h of n is equal to order of 1, hence my u of n is equal to n power r, so n is equal to 1 here. So I can see that t of n is equal to n power log e to the base b t of 1 plus u of n. So n power log 8 to the base 2 t of 1 plus u of n is 1, order of 1 here, so which is equal to n power cube. So log 8 to the base 2 is order of n cube. So you can say that the time complexity is order of n cube. So however, this time complexity can be reduced if I apply the Strassen matrix multiplication. So Strassen has proposed reducing the number of multiplications with the number of, even though number of additions are increased, because multiplication requires more time complexity, whereas addition and subtraction operations are machine operations and they do not require much time. They can directly do with the hardware that is available, so using adder and subtractor. So hence we are having some variables that are introduced, p, q, r, s, t, u, v, and so as earlier we have taken that a is equal to 1 1 1 and b is equal to 1 0 0 1. So I can see that A11, A22, A11 is 1, A22 is 1. So which is equal to 2 into B11, B22. So B11, B22 into 2 is equal to 4. So B11 is 1 here, 1 into A21 plus A22. A21 is this and A22, so 1 into 2 will be 2. So A11 is 1 here, B12 minus B22. So B12 is 0 and B22 is, so which is equal to minus 1. And A22 is 1 here, B21 is this, B21 minus B11 is again minus 1. And B22 into 1 into A11 plus A22, which is equal to 2. And A21 minus A11, A21 is 1 and A11 is also 1, so this entire term will become 0. And A12 is 1 here, A22 is also 1 here, so this entire term will become 0. So I am getting the values of P, Q, R, S, T, U, V. So we are just substituting. P is 4 here, S is minus 1, T is 2, so hence it is minus 2, and plus V is 0. 4 minus 3 is equal to 1. So C11, so we know that C is equal to 1 0, 1 1 1 1. So C11 is 1. So R plus T. R is equal to minus 1 and T is 2 here. So which is equal to 1. So C21 is equal to Q plus S. So Q is equal to 2. S is equal to minus 1. So which is equal to 1. So P4 plus R is minus 1. Q is 2. So which is minus 2 plus U is 0. So 4 minus 3 is equal to 1. So if I observe here, all the matrix C value will be is equal to the 1 1 1. So in this particular scenario, the number of multiplications are being reduced. How many are there? 1, 2, 3, 4, 5, 6, 7. So for 7 variables, I am having 7 multiplications, and of course the additions require an square. So if I simplify this equation using recurrence relation, so I can get this. So an square is as usual, but um, 1 plus up to 7 into n by 2. N might be maybe 1 2 3 and so on up to k minus 1 I can have. So whenever it is equal to, then 7 power k into t of 1. If I simplify this, I'll be having the time complexity, because I can ignore all the constants here. I'll be having n power log 7 to the base 2, which is equal to n power 2.81, which is much smaller than n cube whenever n is large. Whenever n is very large, which is 10 to infinity. So even this one I can calculate with the equation. So t of n is equal to n power log a to the base b t of 1 plus u of n, right? So to find out u of n, I should find out f of n. F of n is equal to f of n by h of n is equal to f of n by n power log a to the base b. So f of n is cn square and n power log 7 to the base 2. So cn square by n power 2.81. So this is 0.81. So n I am having minus 81. So then u of n is equal to order of 1. So I am placing in that. So t of n is equal to n power log 7 to the base 2 t of 1 plus order of 1. So which is equal to order of n power log 7 to the base 2, which is equal to order of n power 2.81. So in this way, the time complexity of order of n cube is being reduced. It seems to be very small value, but whenever n tends to a very large value, it gives a lot of improvement in the time complexity by the Strassen matrix multiplication. So if you have any queries, you please post us, and thank you for watching.